All right. So as of today, basically, your focus will be on model development. That's your next basically milestone. And the first thing we want to talk about is that model management and experiment tracking. Who here wants to tell us what do you think is experiment tracking? What's your definition of experiment tracking?
Basically, like you do a model, you want to test what are the change to the parameters. So we want to keep track of what parameters are working, what is the KPIs.
Okay. What else?
Behavior of my body over number of options that data sets compared to the global benchmarks and the defined benchmark how environment on this.
Okay.
You can compare, suppose you train 3 different models, and you can compare the performance of them, how they performed, score all the parameters, and see a graph like this model performed.
Okay. Anyone here?
More about model.
Model what? Reproducibility. Okay.
If you're probably working with Bayesian models or probabilistic models, you can track like diagnostics like how are your state transitions happening, some really useful stuff, internal model behavior, gradient behaviors and stuff.
Okay. What else? All right. So these are all correct, but you need to unify all these answers, basically. The idea is that when you try to build or work on a project, there are so many unknowns that comes into development. These unknowns could be which model to use, which model, what are the parameters to use, parameters like a hyperparameters, basically. Who is running the experiment or who's running the model? What's the infrastructure we use? What are the basically versions that you use, like a library versions that we are using? And more important that the data itself, which data version we are using, which slice of the data we are using. And all of this will generate some sort of like artifacts. Artifacts are being used later to compare experiments at different time steps to understand, okay, we have this version that is generated today. We have another version generated last week. What's the difference between these two? If they have same performance, could we understand why this model 2 weeks later or 2 weeks later, after all this engineering, is it still as the same performance that the model we had 2 weeks ago? If you have done proper experiment tracking, you should be able to understand all of this. So in general, ML projects basically has far more branching and experimentation than software engineering. Because in software, you build a software, it's kind of like it's really deterministic. You know what you want to build, how you want to build it. And we have been really good at that. But when it comes to ML, there are lots of basically stochasticness in the process. That's, you're not sure. You want to try out different models. You need to try out different hyperparameters, different data transformations. That basically causes to debugging becomes difficult. And difficult means that how often have you worked on a project during a school and something doesn't go wrong, you need to go back, try to figure out what did I do, just trace back your steps. You have done that probably at some point during your school project, right? And that's why, because you didn't have a proper experiment tracking, techniques or tools to use for it. Now, the other thing is that small changes in like ML models can have drastic change, output change. That's actually one of the problems with lots of machine learning models is that you change one parameter and it's kind of like, imagine you're cooking and you just add a little salt, but it becomes so salty. Like you don't know what happened. If you don't track things, you don't know actually why or you cannot trace it back. And the other thing is that, well, running experiments can be time consuming and expensive. Now, what does basically experiment tracking provide us? So it allows you to duplicate results. As one of your friends said that, can I replicate basically what happened? Can I redo it? It's always important if you build something and you reach to a certain answer, you should be able to reproduce that answer. I know lots of time you might hear this thing that, okay, this is probabilistic. We are not sure how to, it doesn't generate exactly the same answer or something like that. That's a really common answer, but that shouldn't be the case. It basically allows you to compare different experiments at different time steps. Like you have two models at different, same data, you want to compare them. It helps you to manage code, data version, hyperparameters, environment, and metrics, and so on. And today, all our labs today are focusing on different tools that you can use for experiment tracking. It helps you to organize experiment in a meaningful way, and also it makes it accessible for other collaborative in your team. Like let's say you have managers and you are basically running experiments, and all they want is to see a summary of what's happening, not all the details that you know. If you have a proper experiment tracking tool, they always have this proper dashboard that shows them some visualization, some summary, who is working on it, when it was built, and so on. So these are some of the points that experiment tracking will enable you for. Now, you all have been working with Jupyter notebooks, right? It's kind of like I personally also work with Jupyter notebooks. There's nothing wrong with it, but the reality is that notebook is not for production. Notebook is good for you to, if you are planning to do some experiment, but that's all. The problem with notebook is that whatever you run in notebook doesn't necessarily will run outside of it. You probably have had that some code that you have runs on your notebook. If you give the same notebook to your friend, also they cannot run it. But there are lots of basically metadata or cache data that exists on the system, and the way that Conda basically gathers this information, that they won't necessarily will run on other basically environments. So there are some of the like cheat codes that you can use for your notebooks. One of them is NB-convert, which converts notebook to the PI file. NB-dime, if you want to see the difference between two notebooks version that you have, that's another thing. GPTeX does the conversion and versioning for you. And there's this Neptune notebook. Have you heard of that? Neptune notebook? It's kind of like some sort of version of the notebook. It's not free, but it has some free licensing also that does the versioning, diffing, and sharing. Now, if you are working with a notebook, and you want to say, okay, all my code is in this notebook and I'm sure it's running, the easiest smoke test is something like this. Just convert the notebook to .py and run it as a Python file to see if it's going to break or not. So that's kind of like a smoke test for your notebook files. Now, the other thing is that you need to also understand that when you work with ML project, it's not just one big file. It's kind of, you have lots of things that you're going to upload, right? So first thing is the modular code. It's you need to be sure that all the codes that you write are kind of like a modular, like a smaller code. Don't write codes that does so many processes at the same time. So those are like a monolith codes. You have collection of independent and version files. So that's another thing that you want to do. And Git helps you with something like that, right? It's kind of like for versioning, for tracing. It helps you with hierarchy and MLOPs, and also it basically has this proper code repository and commits. So when you want to track your runtimes, be sure that you have some sort of like a config file. It's always like for the project for that specific pipeline. Be sure you have some config files that has the parameters that specifically you need for your pipeline to run. And then you have defined some CLI or some command line that you can run the pipeline given the environmental variable or the config file that you have. So you can log your runtime parameters using some sort of like arg parser. Just be sure that you have those in your pipeline. I'm not going to send on the you have done this before yourself. Now, we're going to talk about some of the tools for experiment tracking. First one is data versioning. I noticed that most of you were not part of the lab we did on DVC. But if you feel like you need the lab, we can basically hold the lab again. But the idea of data versioning basically is that you need to understand your data reflects the word is changing, so the data will change. So you need to be able to trace it back and understand, okay, what changed about my data, when did it change, who touched it, who changed it, and so on. Experimental changes include the change in the data, especially in ML, which data is the first-class citizen technique. So you need to remember that concept. And there are some tools for data versioning in the market, like Neptune, Dol, PyCharm, MakeFS, Delta Lake, DBC, Git LFS, and ML metadata. These are all tools, different tools that can help you to. There are more than this, but these are the one that I could search. Git LFS, Git large file system. So GitHub by default is not is a code versioning. It's basically a code versioning repo. So it's good for only for you to push code. If you have data that you want to push to your Git repository, remember something. If your data is larger than some size, and you're using a basically default GitHub, you can easily break the commit, right? Because it doesn't have that bandwidth. If you need to push large data or store large data in GitHub, use Git large file system, Git LFS. You need to register for that basically. It's kind of like GitHub gives you a storage for data. Otherwise, just use DBC or MLM DBC. So in experiment tracking, we say that it helps you also to compare result. So what you want is, doesn't need to be like a pre-built library. It could be a dashboard that you use yourself because you already know what you have been tracking. But what you want is to be sure that you have some sort of like a dashboard, some page that you can compare different runs, and you basically have some parameters that you're targeting, parameters, metrics, and stuff like that. So you need to decide what you want to track and use for comparison. So TensorBoard is another example, which we're going to quickly look at today. So if you're working with TensorFlow, and TensorBoard is like an easy plug tool that you can use. Basically, all you need to do is that to just run it at the top of your code. And it basically what it does, if your code is TensorFlow, it will automatically trace all those hyperparameters, parameters, metrics that happens within your neural network training. So it's and it gives you out of the box dashboard for you to work with. Now, the other thing is that concept of organizing your model. So you want to be sure that you can search and visualize like there is comparison between different models, and these different models doesn't necessarily need to be on your machine. It could be another engineers in your team built a different version of the model, but with the same end goal. And you want to be sure that you can compare those together. So this data pipelines allows you to organize them into some digestible format. It's shareable, and basically it also allows everyone on the team, just access rightly. If you, we will have a lab today with a couple of libraries. One of them is called MLFlow. And one idea you could do for your project or product that you're building is, if you have different team members building the same model, you could basically, and you want some shared repository for free, you have a GCP, build a bucket that you write the metadata and logs of model training every time the model training is done to that bucket. Then that bucket is just some data lakes. You can read it. So you have it, you can build this like a Tableau dashboard that can read from that bucket the data. And if you want to build in-house basically data like experiment tracking tool yourself, you can do something like that also. It doesn't need to be any of the libraries that you are seeing. But all you want is a storage, some metadata that you want to track for your comparison, and then some way to visualize those or summarize those. So this is just the same idea of like if you want to. So here what you see, you have a same project, but you have different owners. That means different engineers are working on building a model. And you have a way basically to compare this model based on accuracy or AUC, whatever is important for your experiment, basically. If you work on GCP, and you're like, okay, directly everything happens on GCP, and you're working with Vertex AI. It also has Vertex TensorBoard that allows you to, without building anything from scratch, you can just use Vertex TensorBoard for experiment track. Okay, so that's another thing to keep in mind. Now, it's important to understand that similar to everything that you have seen up to this point, experiment tracking is also iterative. So you can't just start the experiment. I'm trying to build a model, and you assume that it's going to be done in one iteration or two iterations. It's an iterative process. That's why you need to have a way to compare a result to understand which direction you go is the correct direction or is the wrong direction. Especially if you do hyperparameter tuning and you don't know, okay, should I increase the range? Should I decrease the range? Should I add new values? How could you see that? So one of the ways that if you have a proper way of visualizing it or maybe summarizing the result of your hyperparameter tuning, you can decide, okay, maybe I need to expand the range of this, or maybe I need to do a different searching technique, basically. We're going to talk about those during the lab. But as part of your experiment tracking, you need to first thing is define a baseline. What does that mean? If you start to working on a project, you want to build something, a model. What is your baseline for that model? The baseline could be coming from some already done study that you are showing that, okay, this is the baseline. Like, for example, when I was working in my previous company, we were basically doing some sort of like sensitive document labeling. And we knew that by default, humans are 92% accurate in reading medical document and label it if it's sensitive or not. So, and that was a number that was available. So we were using that as a baseline, that minimum that the model should perform in order to even be considered as a good model, right? So that either is in domain knowledge, something that you are aware of, someone has done that study, someone in your company, or you need to just come up with a model that you're like, okay, this model is simplest but the strongest model that we can use. And if I, like, for example, logistic regression is a common baseline we use for so many classifications. So if you're like, if I have a logistic regression that gives 90% accuracy, and I'm doing a neural network, it gives more expensive model, it gives 91% accuracy. So is it a good model or not? Probably no, because you spend lots of costs on neural network, but a simple baseline model can basically outperform almost, right? So you need to start with the baseline. Be sure to develop, implement, and evaluate, some sort of metrics. You probably have done that, I think so, as part of your scoping. Define your metrics. What are you targeting for, right? So that's good, something good to have. If your metrics are business metrics, remember you need to find some sort of like a proxy between engineering metrics and business metrics in order to meet in between. Okay, that means if your business metric is that I want to increase money, like raise money or basically increase sale, but your engineering is like, well, I don't understand how to build a model for that. So you need to figure out how you map these two together. Then you need to assess the result and decide on the next. And all of these, you need to consider latency, cost, fairness, etc. Why is important? Doesn't matter how good is your model. If it's the model they built is so heavy that you cannot run it, it's like it takes a long time to run, then it's not going to go anywhere. So especially for small scale types of product. We're not talking about something like a ChatGPT that you have infrastructure of hardwares that they can help you speed up the process. For something that you work on, you need to be sure that this can run within a certain time window, latency, CPU, GPU utilization, and so on. Okay, that means if whatever model you come up with for your product, and you're like, this is really good, but when you want to work with it, user asks a question or user send a query, and it takes a minute or two, and it's supposed to be an online model, then that's not acceptable. So if it's a batch processing, that's something. Batch processing means user can send a query and they are not in a rush for the answer. They can come back later. Like when you go on your bank and you submit a request, then they give you an answer that we will let you know within the 72 hours if you were approved or not. right? Because it's batch. But if you go on a website and you are trying to, I think your project, if you're trying to answer a question about a hotel, user is in a rush. I have a short amount of time that I want to use for searching for the hotel. I want quick answer. Every question that they ask, it takes a long time to get the answer back. You probably will lose the customer. Okay, so just keep those in mind. So that means when you build a model, keep that in mind. It's going to be part of the bigger system. If you have a low latency, even in the model inference, then you will have a lots of longer latency in general, like as a total pipeline. So another library that we will look into is called weight and biases, which these days is kind of like a more popular. It's basically it has some benefits similar to the MLflow that we are going to see. Surprisingly, it has a limited trial, which something like MLflow is free out of the box. It does everything almost the same, but weight and biases they have a limited trial. Although if you apply, I think with your Notisten account, you can get a student license. So it also provides you a dashboard, something like this, that it allows you to compare different runs. We will see something like this, but in this part of the dashboard, what you see hyperparameter optimization. So you have basically you have different parameters, different hyperparameter, and each of these axes that we will see later are one hyperparameter. When you do hyperparameter tuning, your model need to find a combination of those hyperparameters that gives you the best result. Why something like that will be important is, again, I'm just going to go over it later, but if you find the highest validation accuracy here, see on the top, and trace back that line, the yellow, and that yellow tells you the loss was 0. Here, the RS was, I don't know, like some 0, 0, epoch. You need to find which epoch is this, and then you need to find the dropout. So it tells you that basically if you have a dropout of, I think the number is 1, drop of 0 or 1. But it tells you that which one of this, we can't see it on this image, but it tells you that which one of these lines led to highest basically a score. And you trace back that line and you might reach to a hyperparameter and see that the hyperparameter is at the minimum value that I as a range assigned to. What if I go lower in that range? Will I get an improvement, right? So this summary is something like this. It allows you to see the range and the for your hyperparameter and how they connect to the final performance values that you have. All right. Any question on that so far? Okay. So, introduction to MLOPs. You're like, I've been doing MLOps for 2 months now. That's the introduction. You're going to see that. So first, we want to talk about the difference between data scientists and software engineers. All right. So data scientists, it's all like more like people that work on fixed data set. What does that mean? You have a data set, company has a data set, you ask for the data team or backend team, hey, can I get data for this? Or you write a query if you have access to it, and you get a batch of the data, fixed data. This data does not change, not dynamic. So you have a fixed data set that you're going to work with. Then your focus is on model metrics. Your focus is that I need a really good accuracy model or whatever is the metric that we have because I need to give it to the boss. If you're your own boss, basically you're like, I need the highest accuracy model. So your focus is just around the metrics of the model and the model basically accuracy. You prototype on the Jupyter notebooks. That's a reality of it, right? So it's kind of like a really rare to see actual code. When I do, when we receive interview candidates, one of the things I always look is GitHub, and lots of when we have especially engineering position, and when I look at the GitHub and I see that everything they uploaded is Jupyter notebook, I'm like, okay, well, I don't see any sample file that shows that you know actually how to code like a software engineer. just Jupyter file. So that also keep in mind. Your GitHub, be sure that you have some sort of like a examples of your Python coding or your coding in general, not just Jupyter files uploaded. Then basically, they are normally the data science are expert in modeling technique and feature engineering, because that's the core definition. Like really good in doing feature engineering, come up with the statistical like analysis, building new features, and then building a model itself. They don't care. What they don't care about is that the model size, cost, latency, and fairness. Because normally with data scientists, which again, this is kind of like a generalization, but it has changed over the last specifically 2 years, because companies now, they require data scientists to do lots of around like deployment, or basically do a lot around like fairness analysis and stuff like this. So things has changed a lot in the industry, but in general, the end goal is that to build something, deliver it to a next team that they're going to test it and deploy it. On the other hand, software engineers, basically, their focus is on to build a product. They're really concerned about cost, performance, stability, schedule. How does this run, basically? The focus is on identifying the quality through customer satisfactions. As a software engineer, when you build a software and a user interacts with you, you will be part of that customer-facing calls if customer has issues, because you really care about this. You want to be sure that you build something that scales. It can help handle a large amount of data, right? Again, the data scientist, that's not your goal. I want a model. I don't care about the rest of the pipeline, how it's being used, who's going to use it, and basically how we utilize it. You need to basically focus on detecting and handling error condition, some sort of like some sort of automation also here. Like if you think about also, they also consider about the CI/CD, which unfortunately data scientists, we also did that. They consider requirement for security, safety, fairness. On the other end, basically, they want to maintain, evolve, and extend the product over a long run. Again, no offense, but normally when we work with this data scientists, it's like a project to project. I build this, I'm done, I'm on the next project, I deliver the model to a different team. Well, when software or ML engineers, they work the way is that you work on everything, and I build this, I'm going to be assigned to this project as it goes, unless there is a need to someone else replace that specific task. Now, because of this gap between data scientists and basically software engineers, there was a growing need for, okay, we need to do more like ML engineers or MLOps, basically, because now we have large amount of data set. They're kind of like, we have inexpensive on-demand computer resources like cloud resources. There are lots of increasingly powerful accelerated these days, like GPU, NPU, TPUs, especially if you work with GCP. Again, the TPU is pretty amazing. Then rapid advancement basically on ML research also. There are lots of research that happens in ML that companies are quickly wants to convert it to a product. So you need some team that's can do all of this now. But before, if we could just cycle back, like during the 90s, software engineering basically was silent. Right? There was an era that software engineering was pretty bad, and that was before the concept of the CI/CDs and stuff like that, because it wasn't scaling. It was pretty slow. It had lots of errors coming out of the product. No one could have cached them early enough, and so on. But what happened basically was that there was some improvement, especially the idea of CI/CD, and then over time, software becomes one of the strongest basically things that we have. This is all the companies, they specifically have a software team because the practices are kind of like a design and are already known. That's kind of like a machine learning these days. Lots of us, they build a model and before it being deployed, it being blocked. That's a common thing that happens. I think the recent Gartner, and if you follow the Gartner's basically analysis, 3 years ago, 88% of the data science projects, basically, they are just remain as a project. They build something and that's it, disappears. And this year, they did the same study for AI modeling, and 95% of the projects across the industry that they basically did their study, AI product that the companies built, that's it, died. 95% of the AI product this year, all that money died. Why? Because there are lots of things that you build, but it doesn't necessarily mean it will work, right? So the idea is that it's sort of like these types of modeling that's building is normally slow. There are lots of manual tracking, lots of components that you build change. You need to be sure that you can track. Sometimes you don't have the bandwidth or the engineering for all of this. No reproducibility or provenance, inefficient collaboration, unmonitored models. There are lots of issues that causes ML or basically AI these days to easily fail. So it's important to be sure that we need a team that they can understand and they can basically take care of this. Now, we also talked about this before, that we need to bridge the gap between software and ML. The idea was that, well, we keep the CI/CD as it is. We're going to add CT and CM, which makes sense. It's continuous training because the data changes, the new data comes, customer changes, word is changing. Well, you need to also train your model to adapt to those changes. And continuous monitoring, because you want to be sure that you monitor constantly this pipeline. So if something happens, you can detect it early enough to avoid some sort of like cascading effects. Now, if you put all of this together, you can find the similarity or where the ML engineer roles basically come. Experimentation development is data scientists, ML engineers. Continuous training, ML engineers, data scientists. Model deployment, ML engineers, DevOps engineer. And continuous monitoring, ML engineer, DevOps engineer. So if you see that in industry, that like the need for ML engineer roles becomes really popular and the interview process becomes more like they have listed almost everything. It's the idea. We want engineers that they work from the beginning of the project with the data scientists or basically with the scoping all the way to deployment and monitoring. So you basically need to put different hats on as an ML engineer. Now, the idea is that we want to standardize the ML process using MLOps. That was the whole idea of like MLOps. So you want to standardize the ML lifecycle management, model versioning and iteration, model monitoring management, model governance, model security, model discovery. You want to be sure that you have a system in place, set up practices that you can standardize all of this in your company, okay, or in basically in your team. Now, when we talk about MLOps methodology, so we're going to start with the definition called MLOps level 0. But what is an MLOps maturity? So there's a term, MLOps maturity. Basically, it tells you that this is kind of like a degree of maturity a company has in the ML pipeline. How mature is you for applying some of the software practices plus MLOps practices to your pipeline or to your team or to your basically company? That defines the degree of maturity that you have as an MLOps. So the first one, which we say MLOps level 0, which is probably everyone in the school. Right? It's like what we built in the school as a project. It's kind of like you have a local data set on your computer. You do some manual experimentation, data preparation, model training, model evaluation, and you do some model analysis at the end. The result of this is that you have a model, correct? So if you go to a company that they have an MLOps maturity of 0, that data science team or that specific team, even ML engineer team without maturity, they always work in silo. They build something, and when it's done, they put it in some storage and send a message to IT, DevOps team, whoever is responsible. Says, okay, I have a new model, go deploy. There is no proper tracking, like a giving information of how to run it, basically what's the pipeline for it, how to test it, and so on. It's just literally like a silo work of handing over the model, throwing the rock on the other side of the wall. It becomes someone else's problem. Now, so there are least frequent releases, no CI/CD, so no, basically there's no testing, there is no deployment. Basically, there's no way of monitoring performance. You develop a model, you say, this is the good model, we develop, we test it. But there's no way to have a place to compare this model with other models, or basically like doing experiment tracking. It's just a model that you build. Normally, when you work in teams like this also, everyone gets kind of offensive if you say, have you tested this way? Or does it work? Or why it works? As soon as you try to question, it's kind of like it becomes kind of like a heated conversation. Because people think of this kind of like an attack on the basic knowledge, despite the fact that it's kind of like it should be generic questions. So challenges for MLOps level 0. So you need to actively monitor the quality of your model. You need to retrain your model basically with new data, and you need to be sure that you can do continuous experimentation. That's where MLOps level 1 and 2 comes. Also, majority of the market is MLOps level 0, even at the current time. We're not talking about large companies. But especially when you go to startups, it's MLOps level 0. You build something, you want one thing to work, you don't think about the future. You just want to deploy it as soon as possible. The idea is that quick. So no one builds the pipeline. Everyone just build the model, deploy it, breaks after a month, redo something again, you just reply, basically redo the same process over and over again. So then we go to MLOps level 1 or level 2. The idea is that by starting with the rapid experimentation, you need to have a way to quickly do experiment. And basically that means that you need a pipeline for data validation, data preparation, model training, model evaluation, and model validation. That pipeline should become end-to-end. The only thing you change is going to be your data over time, basically, and you should be able to quickly experiment. And the result of this, the code, you basically write it to some sort of like a source repository, or GitHub, for example. Now, when you pick that and put it in a bigger picture, the same orchestration experiment that you have on top will be reusable. Then you can use it as part of automation pipeline. So here, basically, what we see after the orchestration experiment, source code goes to a source repository. That's where the MLOps basically comes, ML and ops part. So over there is a connection to your automation pipeline. That means your pipeline, we will need to talk about that, but basically the code comes to your automation pipeline, the same code. Here in this example, there's a feature store. You can read the features or data, process data from. The result of the validation model would be a model trained, and that model you will need to store it somewhere. So that's where you define a model registry, and that's basically what we saw on GCP Lab, right? So it's kind of like some artifact registry for your model specific. The trained model basically goes as part of your CD, which is model serving. It goes to your prediction serving. Then you need to have some performance monitoring, and the performance monitoring will trigger the pipeline again. All right, so this is just a general. Now we need to break this down. So to start with the CD or model serving. The idea of model serving is that you build a model and you want to serve it, right? But you don't want to also do this manual. So you want to be sure that you have some set of like some code, let's call it for the moment, which whenever there is a new model added to your model registry, your model serving CD, continues basically the delivery part or the deployment part, basically picks that one model and runs series of basically tests. Specifically, we're going to talk about that later today around the infrastructure that you are targeting. Speed up. It's kind of like a last test before we deploy it. And if it passes all of those, then you deployed, and that becomes a prediction, gives you a prediction server. It depends where you are deploying it. That could vary. Then the components that you will see right now, data validation, is going to be the same. Whatever your team built as part of orchestration experiment, the same component need to be reused in your automation pipeline. So there shouldn't be discrepancies. That's really important, because you could easily build something and there are a couple of lines difference in the code. We just made it better for this one. No, you want to be sure that you're using the same code to avoid any discrepancies that could happen. When it comes to model validation, the strategies you use for model validation, picking the model as part of your experiment, they should be the same strategies you are using as part of automation pipeline. Okay, again, no discrepancies between the techniques you are using there. Always should be the same thing.
So the automation pipeline is for automatically retraining.
That's correct. So what you see here, prediction server is connected to performance monitoring on the bottom. Performance monitoring connects to something called a trigger, and the trigger connects back to automation pipeline. So performance monitoring, we will break this down as we go through these upcoming classes. Will be a part of your pipeline that does series of statistical analysis to decide, okay, should we train a new model? Should we retrain the model, sorry? Or if it's like a really bad and something that your result shows that you cannot do retraining the same model, then you need to basically build a new maybe generation of model or change your scoping about the model that you have built. Then you have feature store, which the idea is that during the orchestration, you have learned, okay, we need this, we did this feature engineering, and we also learned that some features are expensive. We shouldn't basically build them as part of like a online data. So what you do, you build a feature store that you pre-compute set of features that could be used by your data pipe or by your automated pipeline. That's the idea of the feature store. So if you know these features are useful, just build them, store them in some database that you can use those later. And finally, the metadata DB, it's where that when you have this automated pipeline, and we had this in the previous lab, you need to ensure that you collect enough metadata about the experiment, about anything that's running in the pipeline. And that's your decision what you want to collect as a metadata. But if you collect metadata, you need a place to store it. Some place, some sort of like a metadata store that is easily accessible for read and write, because your pipeline will use it. But it's also something that you can search against, like do a query to do comparisons. So when you decide on your metadata DB, think about like the metadata that I'm storing, do I need to be able to quickly read and write from it? Or is it kind of like, it doesn't matter if I can, like it's not online, maybe it's just a batch. If you need something that you need to be quickly able to read and write, so you need to pick types of, storage that has that, read optimized capacity. Otherwise you can have this delay always. Now, when it goes to MLOps level 2, and again, this level definitions is not like it's kind of like an industry level, industry accepted definition, but it's just gives you a bigger picture. Is where you introduce the MLOps practices as some sort of like a CL, CI, basically CI/CD, CT, CM in the picture. So here, you have the orchestration experiment pipeline that we saw before. Automated pipeline is the same thing replicated. But after the source repository, where your code goes to your GitHub, that's where you will have CI, continuous integration, which the idea is that it will build, test the code as a basically source code. And if everything passed, then it will package that code, send that code to a CD pipeline. And CD pipeline, as we discussed in the previous picture, it does basically additional tests in infrastructure. We need to talk about that. And then basically send it to your automated pipeline. Maybe the result of your CD pipeline is going to be, for example, a containerized package that you ship it to your GCP basically Docker Hub or your GCP basically artifact registry. So you send the result as of the package, a container, to some repository that your rest of your pipeline read from that repository to run the pipeline, run the code. So that's the main two differences that you see. Here will be the trained model and the MLOps basically packages. All right, so if you put all of this together, for your product, what you're building is going to have something like this. Starting from top, you do some experiment, basically built up like an experimentation on building some package, some code. When it's done, and when you push that code to your GitHub, that's where it basically becomes your code repository. That code repository, as part of your GitHub, you're going to have Git actions, right? Part of, and then if you are using GitHub and Git actions, for example. But then that will basically start your CI/CD pipeline. As part of your CI/CD pipeline, there will be some tests, and the result of that will be an artifact, kind of like a container. That you need to push to some artifact repository. When you write to artifact repository, you have another part of your pipeline that is listening to that artifact repository, kind of like, or you trigger it as some sort of like a trigger push, that there's a new container, there's a new code, pull this new code. When that happens, the continuous training happens. The training pipeline starts because now there is a new container, or there's a new code, or simply there's a need for retraining. The result of model retraining will be a model trained model. That trained model, you need to store it also in some repository. That's what it calls model registry. You need a repository that can track your models, but based on some sort of like, you have some metadata and versioning style that for storage, model storage. Then when you have a basically a model added to model registry, then that will trigger a model deployment. Now, model deployment itself, so you have up to this point, what you had was CI/CD for your code. But this part, after you have a model, becomes CI/CD for your model. The focus is that first, test this model to be sure that, okay, this is like a past series of unit tests, result expectation. Then the second set of tests happens that check if this model can run within certain time seconds. Because you don't want to all of a sudden deploy a model that's super slow. So you already have a predefined boundary for time, CPU, memory utilization of the model. Then you also need to target environment. If you build a model that is supposed to run on Windows, you need to test it on a Windows machine. If you build a model that's supposed to run on Windows, Mac, Linux, you need to test it all three. So the part of the CD is going to test the infrastructure against the model. So your model against the infrastructure to ensure that it can, basically you need to mimic the exact infrastructure that you're targeting to deploy a model. Okay, if it passes that and it's like, okay, you know, all this test, and also you need to test it against the previous version of the model. Is it actually better than the previous one that we have? You know, and how much is better? It's like if you need to have some basic decision also. And then if it passes all of this, then you do a model deployment. That model deployment basically goes to some sort of like let's say you have some sort of like a service, Kubernetes, cloud function, whatever you use for deployment, the model starts running. Then you need to basically start serving and logging. Now we're going to talk about, break this down today also. Okay, after deploying this model, how should I serve this model? How quickly should I make it publicly available or accessible to my customer? Should be all of a sudden everyone has access to it, or should it be like a gradual access? Okay. Any question? Everyone is going to deploy all of this? All right, great. So now we're going to talk about, I think we don't need to talk about TFX. We already have talked about this. Let's talk about managing model versions. So when you build model, especially you're automating this pipeline, you need to have a way to store the model and version them, you know. So you need to have a schema for versioning. So the idea here is that different teams will work on the, you know, same project, and they basically especially when it's come to coding, you have a proper version control, correct? It's like a GitHub. It perfectly controls it for you. But when it comes to the model, it's not just the code that you need to use for versioning your model. You need to use code, data, and configuration for ML models. So the versioning shouldn't just tell you which version of the code it is, which version of the code, which version of the data, platform, or configuration. Those are part of the model versioning for ML. In software, it's a common practice to follow this schema. Major, minor, patch for versioning. Every time you download something, it has major, minor, patch version, right? It starts with major, which is the first number that you see. It normally contains incompatible API changes. So whenever you see a product from version 2 to went to version 3, that means it's incompatible. You cannot reuse between components. If you have a previous code that's run on version 2, and example of this was the Airflow lab. On the GitHub, we had the version 2. In the class, I did version 3, but none of the codes from version 2 runs on version 3. So we basically we ended up redoing all the code to match to version 3. So it's incompatible, basically, changes. Then you have minors, which becomes the second number. And that's where you add new functionality, but there is a backward compatibility. Okay, that becomes normally the minor. The last one in software, basically, we say is like a patch. And that's where you fix bugs. Someone creates a bug or there's a request and you fix the bug and you increment the patch number. So when you see these changes between numbers, it tells you what was changed within that software release. It's just a patch, or just some additional functionality, or is it just a total incompatible changes? But when it comes to machine learning model, there is no actual way or industry level accepted basically schema for modeling. All companies technically do whatever it makes more sense for them. One of the recommendation idea is that do something like major, minor pipeline. Major is when you have incompatible data type or like a target piece. It's like something that the nature of the pipeline has changed. Minor is when the model performance improves. That means if you have a new model that is doing better and you want to use that, you increment the second number. And pipeline, or the third one, is when you basically your pipeline is changed. There's something in your processing has changed, and you basically want to use this pipeline, but the model basically, you know, it's like the improvement or something is the same. So you just last number increment. Again, it's not like a different companies, they do this differently. We were basically previously we were doing something like that. Our major was when we used different code. Basically, we were using PyTorch, and then we went to TensorFlow. Same idea, same product. So that was our major changes. Minor, basically for us, was that when we improved the model performance, and we didn't have a technical pipeline definition, but we were focusing on the data processing, like the types of features we use. Again, different companies, they will have a different way of basically versioning this. For your product, what you need to do is that come up with a way that you're going to version, because you need to send your trained model, or basically even if your model is not a trained, it's like a pre-trained, so you bring it from somewhere else. For your product, need to have a version. Which version of this is you are using? This version could be someone else's model, like let's say you are using a Llama 3 you downloaded from Hugging Face, but as part of your pipeline, you need a version for your basically ML pipeline. Okay, total ML product. All right. When you have this proper basically ML frameworks, it can leverage to access the previously trained models. It should be able to, and it also should be able to internally version models for you. Okay, so you need to be sure that you have, as part of your pipeline, you can do that. And again, we talked about data lineage before, which basically tells you that everything that happened on this data, whose data is where it is. Model lineage also, you want to have something like that. Code, data, configuration. And the result of that, it will become an artifact, which we saw in the previous class. Artifact requires a place for you to store it. So artifact need to have a proper information that collected about that specific version, time, who developed it, and so on. And you need a basic metadata store to track it. That gives you a capability to have a proper lineage over your models. Now, when we talk about let's take a quick break. So like everyone. So we talked about model registry and we talked about model versioning, but the important things for you is that to understand, okay, I have this trained model which contains metadata, artifact, parameters, and the model file itself, and I will send this to a model registry, but within the model registry, how should I tag this? Because model registry is a place that you can read model from, and there are going to be different models. It's kind of like a repository, right? Centralized repository. But doesn't mean that if I send a model to model registry, the pipeline should read it, and just basically deploy it. Now, so what you do is that when you build model, there are three basically a stage we're going to define. Staging, basically a step, production, archive. A staging is when you have a model that is a candidate to be the next model. So we call that a stage. So when you send it to your model registry, you tag it with a staging basically label. Then you have production label. That's when the model which is in the registry, like a staging, has passed all the CI/CDs, tests that you have. In comparison with the previous model, is actually doing better. Then you want to promote it to production. In that scenario, you need to be able to change the label of the model from staging to production. When the model goes to a production, that's when you basically pick this model for customer serving, basically. The next one is archive. The model that previously was in production need to basically be retired. So basically you change that to archive. You don't remove the previous version of the model. We're going to see it today, because what if something broke and you need to quickly use it? So you need to be sure that you keep track of your previous models. So now, as part of the model registry, we say that also you keep track of your model versioning, artifacts, annotations, or link to other Visco artifacts, whatever is necessary for you. But in general, your model registry allows you to do model search, discovery, understanding, approval or governance through basically a process of like, do we approve this model or not? Collaborative discussion, streamlined deployment. If the model went to production from a staging, there should be a pipeline that picks it up and basically deploys it. Continuous evaluation, monitoring, and a staging and promotion. That's kind of like what are the capabilities of whatever model registries you are using should be capable of. Now, there are some examples of model registries that you can work. If you work with Azure, it has Azure ML model registries. There's a SAS model manager, ML Flow model registry, Google AI platform, algorithm. There are more tools in the market that they help you with all of this. Or you can just do all of those manually. Now, let's say you have a model that this model went from staging to production, and you want to pick this model and serve it. The question is that how should we serve this? Should we just, again, right away give it everyone access to this model, or should we make this a slow process? So the first thing we need to talk about is called continuous delivery. So Actually. No, let's go back. I think this is like supposed to be CICD. So sorry, going to get back to this. Let's actually talk about CICD. The table was wrong. Continuous integration. What it's supposed to do, your CI. Triggered when there's a new code in your GitHub. So that's the first step in your Git action. There's a trigger, it's like, okay, new code, either pull or push or merge. It will build package, container, image, and executable. It will perform series of unit tests and integration tests on the component, and it delivers the final package to your CD, continuous delivery. Your continuous delivery picks the final package and mimic the actual environment that you are going to deploy this to. So basically, deploys the code into target environment, like it's kind of like a sandbox environment. It ensures the compatibility of the code and the model with the target environment. So again, if you're targeting OS, does this code run on the OS? Or does this basically model runs on the like a Mac OS, sorry. And then it checks for prediction service performance. If this model performance, like accuracy, I don't know, speed, is it acceptable even? Like we have a definition of acceptable. Is it acceptable before we try to deliver this? So this basically, you can put all of this there. So you have the CI, and then you will have your CD, continuous deployment. And then you have model serving, and you will have basically model monitoring. When you do unit testing in your CI, in ML, basically, you need to unit test for your data and unit test for your model. Okay, so your model and the data need to be unit test. You have a fixed example, you expect the model to perform, generates this answer. So you do basically unit test. If your model has some stochasticness in it, you can define a range of values. Okay, it should be between this and this, not like with a small amount of error, basically. If it's deterministic answer, then you have a deterministic basically expectation. When it comes to input data, you need to part of your CI basically to test your input data for feature engineering. You expect the pipeline to do this to the following example. So the expected output is going to be these features. You need to test the values that it generates, and you need to test the format. Whatever it generates as a format, it should be a valid schema. So that basically becomes the CI part of your input data. When it comes to your model, you test the model methods. If you have a model method, means that if you have a, let's say you have a scikit-learn model, you train the scikit-learn, and as part of your CI, basically it saves a model. The model itself has sub-functions as a methods that, as like when you have a saved model, when you load it, it has a dot predict, there's a dot print, and so on, right? It has a series of functions. You need to test those methods if you are utilizing them and you expect certain behavior from those. So if your model in the production, your pipeline uses dot predict or dot predict batch or dot something to use it, you need to test those methods to ensure that it's still there. It hasn't. It's not like a broken. So test the model performance metrics, and then also test to avoid and let's get NaN values or empty string. So be sure that your model basically does not produce NaN values. So also, like the last one, test to avoid inherent bias. So if you have a bias test that you do in your part of your pipeline, it always should work for all your basically new model topics, not if, when you have it. It should be a concept. So when it comes to unit testing, also there are some techniques like a mocking that we discussed in the other lab. Like you necessarily don't need to actually do certain operation, but you can mock the process. As part of mocking, you need to check for data coverage. That means if you have a data set, find the edge cases and test for edge cases and series of random data points in between. Don't just randomly, like if you have maybe if you have a feature space that looks like this, don't just sample from here. Pick from here, edge cases, and then maybe a couple of this. So a smaller, basically data test which can cover the edge cases that you expect to see. For code coverage, also be sure that you check basically all the compatibility between your libraries that you are using, the versioning and stuff like that. So, when you part of your CD, we need to do infrastructure validation. That means you need to ensure that you're deployable to, if you are targeting to deploy this model on a cloud infrastructure, you need to mimic an environment of a cloud infrastructure, like a GPU-based environment, TPU-based environment. If you are targeting to deploy this model on cell phones, that means you're going to do edge devices. You need to, as part of your CD, you need to mimic test on an edge devices. So that means when you, in your Git action, when you build that environment as part of your, you always start with Ubuntu something, right? Instead of Ubuntu, you need to basically figure out what's this OS on this machine and use that as part of your testing. So just be sure that you account for the infrastructures, GPU, TPU, CPU, whatever you are using as part of your testing. And then something like a TFX infra validator basically helps with that. We're not going to talk about that. Now we're going to model delivery. So we're going to start with progressive delivery. Basically, the idea is that to continuously over time release the model to your customers, not to every 100%. So you start maybe basically by a smaller percentage of the population randomly. So have you ever have this ever happened to you that like a friend of yours says that, oh, on Instagram they have some sort of like a features that you don't have it on your Instagram? That's the idea of continuous delivery. So there's a feature you're not sure that should we release it to public or not. So you randomly select a cohort and share it with them. There's some decision on between how to share. You normally want to share it. If I receive it, my friends should not receive it. You don't want to bias the opinion. So based on, like I think Instagram based on like how is there a chance that I know you or something? Basically, based on that, they decide who will have it, a specific cohort group, and that also the decision making behind it. But you can start maybe with a slow progressive delivery. So basically that helps you to decrease the deployment risk. It makes the basic deployment faster, and you basically do gradual rollout and ownership. Now, there are also complex model scenarios that basically you have multiple models, you're not sure which one to use and stuff like that. So you can use the techniques like A/B testing when you have two models, you want to figure out which one to use. Or you can basically do something like a shadow models, a bit like a canary testing. I'm going to talk about this now. So there is basically, these are just a definition of progressive delivery and more like advanced deliveries and shadows. But the actual terminology for in software, the one that happens for the model delivery, first one is blue-green deployment. So the term, like if someone tells us, okay, tell me the deployment types, the first one is blue-green deployment. Kind of like easiest one. In this version, you have a code version of a model version, blue, something that you already have, it's working. Then you have a new version, green. As part of the blue-green basically deployment, you have a load balancer, which is responsible for distributing the traffic. So load balancer, what it does, it basically routes the traffic from one version to the other one. If something went down, quickly reverse the traffic to the previous version. So if you choose blue-green deployment, your previous version is still deployed. You just don't pass traffic to it. But if the current version, something went wrong, you just quickly, all you need to do is that you reroute the traffic. So there is no downtime. All right, so it's kind of like a safe bet if you're not sure or there's a risk with your current deployment. Then you have a canary deployment. So, you know the idea, like in old days, like old movies, probably like cowboy movies. Old when I was a kid, there was like someone works in a mine, and there was like this canary that when they go to the mine, they take the canary to the end. So when they work in the mine, the idea was that they put the canary at the end. So canaries, they can smell gas so quick. So when the canary starts basically screaming, or like it's kind of like inhuman version, but then that's what they know that there's something going to happen. They need to escape the cave, or basically the mine. So that's the idea of like canary testing. It's kind of like you want to be sure that you can quickly detect if something is going to go down. So in canary testing, you're going to slowly release a small percentage of traffic to some new basically code. So the new, everyone is using the old model. Maybe 5% of the traffic is going to use the new model. And you monitor that precisely to ensure that there's no fire in the house. If everything works in the idea of canary deployment, you start gradually increasing the traffic to the new model. And you just keep monitoring. If everything works fine, then everyone, the entire population will access to the same version. So that's the idea of canary deployment. That's correct. So canary deployment is a type of progressive delivery. The other one is like a live experimentation, and this is kind of like a you have some sort of like a model, especially like in recommended model, and let's put something like this, and like you're not sure which one of these two models to use. Like you have a model that works really good, you have a new model there's some recommendation of this will work, but some of those recommendations are like a subjective. You might give a recommendation that technically looks really good, but user doesn't accept it, right? So what you want to do is that you basically divide your users into two groups, A and B, and you randomly basically reroute the traffic to A versus B. You look at the business result of this, not the model metrics, business result, because we were doing a recommendation system. If they use A or they use B, overall, how much we had sales, for example, kind of like from sales perspective. So you look at the business metrics instead of model metrics, and you decide, okay, model A is better than model B. It's not that straightforward. The A/B testing, it has much more to it, but it's like you need to basically randomly assign certain group or cohort to the model A and the other one to model B, and look at the bigger picture in general to see which model works better. That's basically what we do in basically drug discovery. So whenever there's a medication, you create two cohorts and like do A/B testing. One cohort gets medication A, one cohort gets medication B, or they get basically like you check for class effects also. Like they might not even get anything. They might get a fake pill, and then you try to do a comparison. But that's part of like A/B testing. And the next one is like a live experimentation, and it's called multi-arm bandit. Have you seen this machine before? Like you pull down the handle, and basically, if you're lucky, you win something. Otherwise, you lose one. So the idea here is that you have a different basically ML models. Like let's say you have 3 ML models, and you randomly assign traffics to them. As traffic goes, you randomly goes to A or B or C. You monitor the performance of these models, like accuracy version, for example. And over time, these 3 basically keep getting traffic, they compete with each other. The model that start to showing a better accuracy or better performance, you start to increasing the traffic toward that model. And you keep doing that until you get to one certain model that gets all the traffic. It's kind of like you let this model to compete, and you look at the error that they have or the performance that they have, and then gradually you basically increase the traffic models. All right. This kind of like it is another one, contextual bandit. This here basically, the idea will be that it's really similar, but you add some additional context to it, like user could come from a different climates. So it's not going to be just the model goes through, data goes through model, make a prediction. You have some contextual data around the users and where the data comes from. Based on some context, you decide which model is doing better or which model is doing worse. All right, so let's stop here. Zoom on this. Okay. So we're going to start with MLflow, and MLflow is simply one of those libraries for experiment tracking, model registries, and stuff like that. At least it's an open source. So I think they have a paid version also, but for what we want to do, it's free. So let's start with this example. So what you will see here is that in the top part of the code is just imports, but from a line that says import MLflow, so you just need to do pip install MLflow, import MLflow, and import MLflow.scikit-learn. So MLflow has this like connectors to different TensorFlow, PyTorch, scikit-learn, and MLflow models. Actually, before, I think we have a good document. Sorry, yeah, okay, good. So the way that MLflow basically helps you with experiment tracking, so you have something called MLflow run. Whenever you run an experiment, basically, what MLflow does, it creates metadata, tracks it for you, stores it into some sort of like a repository. By default, runs on your machine, so it creates a metadata store, writes everything there. Now, as part of the MLflow run, you get models, metadata, dependencies, signature, some example, metrics, parameters, tags, and stuff like that. So you basically, by default, tracks all of this. Now, when you work with MLflow, there are two ways that you can do the tracking. With MLflow auto-logging and without auto-logging. So auto-logging makes it easy. Like at first you are trying to learn and you're like, I'm not sure what to log. So you just need to turn on MLflow auto-logging. So import it, basically, you just say enable like MLflow.autologging. You're going to see that. And it will track whatever it can, basically. On the other end, auto-logging creates a lots of unnecessary things that maybe you don't want to track, or maybe you exactly know what you want to track. So in that scenario, you basically need to decide on what you want to log, and similar to a simple logging in the Python logging that you write the log lines, you basically write those for the MLflow, and you can log basically metrics, parameters, table, signature, input, model, and so on. So you decide which one specifically to log. So you need to basically decide between those. Now, let's do one example here. So here, basically, we import MLflow. We just generate a random model, like a random forest. And over here, you see that I say MLflow.autolog. So I let MLflow to log everything. Now, you can go to the dashboard that MLflow has. So if you run that, it basically creates a UI, and we open here. So So what you will basically see here is that this is a dashboard of MLflow. So I think this is the older version. I think at this point they're on version 3, which is incompatible. So I did not change anything. What it does on top, there are 2 tabs: experiment models. This is a tab for experiment, which shows different runs. By default, it automatically generates a run name. So when you run it on your machine, and if you see a different run name, that you're like, where does it come from? Because if you haven't specifically defined a run name, it just auto generates text. It tells you when it was run, and then what is the zoom out a little. Tells you the data that it was used. You can click on the data, and if there's something available about the data, like this information, a schema, and stuff like that, it will give you. So you automatically track those. Then there's a duration, there's a source, like it tells you that what type of environment was used to run this. It's in Jupyter Notebooks, which is IP kernel, right? There tells you about the model, that tells you that this model is a scikit-learn family model. So it tracks those. As you go to the right, basically, these are the metrics that it tracks. So like a training meet, R2 score, and so on and so on. And this is like for types of run, like classification, regression, it does auto generation. So it decides on which one basically to select if you leave it on auto log. And then here basically has dashboards. So like if you want to look at metrics, compare different models basically, and then you can basically add to it yourself. Add chart. These are the default chart available on a free version, I assume, that you can use to build dashboards. So depending on what you want to, what's more important for you. Then you can here basically say new run, and you can tell you that, okay, using the same notebook, using prompt engineering, so you can basically add new run, new experiment run basically. Then let's go here. Evaluation. So you can go on a certain run. This is the one we just ran right now. And what you will see, let me just zoom in a little. So basically, you have, as part of the overview, who is basically the owner, where's the source code and stuff like that. But on top, you see model metrics, system metrics, artifacts. So as part of the model metrics, these are the metrics that is available for that model. If it's a regression, so these are the regression metrics that was used. Unless you specifically chose a different metric and you log basically. Then system metric, I don't know if it's by default enabled. Let's see. So no, there's by default system metric is not enabled. But you can basically track CPU utilization, RAM utilization, and stuff like footprint and stuff like that. Similar to what you saw in Airflow metric base. Then artifact. So this is the part that one of the things that when MLflow came out like a couple of years ago, I was like, oh, it's pretty cool because when you work with teams and you're like, you want to deliver your model to someone else. Previously, you need to basically, data science team, put it in a bucket, say to someone else, is your problem now. They reach out back to you and say that, okay, hey, this library doesn't work. What version did you use? Okay, let me go check. And you go do a PEEP or Conda version. It always was a hectic problem. Here, right now, just by simply doing an auto run. So first thing is that, let's start here. So that's the model. And it gives you lots of information auto-generated about this model. It's kind of like the Conda environment was used, scikit-learn, what's the version of the scikit-learn, model UUID for search, run ID for search in this database of the artifacts. This is metadata stored behind it. Signature of your signature that the model expects from input and output perspective. And the time that was created. You can also get the Conda package already built for the YAML file for the Conda, so you can reproduce the same environment exactly. The model file itself, Python package, if someone wants to build the environment with Python, and the requirement file basically. And then it basically also, depending on the library, it has this this file, this estimated .html. On top of that, if you go on the model itself, it also tells you exactly how could you run this model, how could you test this specific model and serve it. So on the right side, basically tells you to validate the model before deployment, and it gives you information. It tells you, okay, this is the address to this model. This is how you can basically serve it. This is also how you can basically do a prediction with it. You can do a prediction with pandas. You can do a prediction with PySpark. So it gives you a pre-built code. Hey, this is the model. This is how you can basically test it yourself. Okay. So, and this is just all happened by auto-log. Okay. So, this is part of your experiment tab. In the experiment tab, again, you can do a comparison. So you can pick two and you can say compare. It basically allows you to compare different runs against each other, different model versions. Basically here, like so the copy X is not an important column, but one thing we can see, training mean error. So on this one is a higher training mean on the right. So you see the red line. And that one maps to alpha of 0.1. Right? So that tells you basically comparison that, okay, if you pick the larger alpha, you end up with a higher basically error. Yes.
So for each run, you should not do hyperparameter tuning like multiple models within each run. So you're supposed to split it up.
No, actually that's good for. So hyperparameter tuning is, let's say I want to build a neural net, okay, and I have 4 layers. So let's say you work on this project, you build a model for classification, and the idea is that let's build 3 types of model: the neural network, generative classification, and a discriminative classification, but like a classical model, like a naive-based logistic regression neural network. So there are 3 models you want to build. There are 3 engineers. Each engineer, so let's say the one that works on neural network, there are a series of hyperparameters you need to figure out, and you don't want to do that manually. So you do hyperparameter tuning to develop the best neural network for this task. Someone else that does logistic regression or naive-based, they do maybe something similar to find the best for their version. The result which comes to here, you compare against each other. And we're going to see the hyperparameter tuning right now. Yeah. Okay, so and here basically you can change the parameters that you want to do a comparison against each other, which feature and stuff like that. It's kind of like a easy platform to basically work for. Okay, so let's go here. Need to stop this. So now in the next line, basically it's just an example of if you decide to define the experiment yourself, like you want to set the experiment rather than being a random experiment generation. So here basically you can say that I'm running a code. I want this code to run under a certain experiment definition. So basically you can say mlflow.set the experiment, and you know the experiment ID because it's a storage. It will add it to that specific experiment. So because you might have a central repository for different experiments, you want to show that this code only adds to that specific experiment. So I'm not going to rerun this. This is exactly this. I'm just rerun the same thing exactly, and you can just start the dashboard again. But let's go here. So this is more important. Now, what happens when we run MLflow? So on left, in your environment, you will see a folder, hidden folder called ML runs. And that's that storage, that local storage on your machine that keep tracks of the metadata, artifacts, and everything basically. So inside here, you have there's a trash, not important, 0, because the default experiment is 0. So within that, those all different runs, the UUID that you see. So here, this is a run. Within that run, and the folders that you see within the what stores on your machine, it's exactly what maps to what you see on the dashboard. So on the dashboard, you saw artifacts, parameters, metrics, and stuff like that. What happens in the background, they save those, store those into like a storage, like a metadata store under, for example, artifacts. Within the artifact, that was that file, the HTML file. Then you have model. Those are, remember, those are the files that we saw basically for the model. Then if you go to input, it tells you that what was the input, what's the metadata around the input. You know, it's kind of like whatever they're collecting, and so on. And this is like comes back to what we saw in the previous lab. And I told you that if you work with something like MLMD, for example, and you know what you want to collect, you can build your own pipeline. Like these are the artifacts that I want to connect, and these are how to combine together. And that basically remember that we had the definition of context, which was the grouping of artifacts and a run. 0 here is that context. Artifacts are the files that generated, and the basically the experiment or the event was is the run number that you have, the UUID that you have. They group together under this context basically value. On the other end, if you go here, so we have parameters, tags, metadata. There is nothing about the model itself. So what does that mean? So you have the model file and stuff, but what if I want to register a model? Like as you run, you want to register the model and start giving a different tag, staging, production, and so on. So by default, this folder is empty. You have it, models, but it's empty because there's no registered model in the environment that you're working with. So in order to register a model, we do something like this. So again, this might have certain changes because if the MLflow has gone to next version, but I'm not sure about that. So you import MLflow again. From MLflow.models, import infer signature. So that infer signature basically is a function that you use to this is a model that you have. This is the output of the model. Basically using this infer the signature of the relationship between input output. That's what infer signature does, which MLflow autolog does it for you. But infer signature basically says, given the model input and given the output, what is the signature for input output relationship from the model? It's kind of like it does a reverse mapping. So what we do here with MLflow start run as a run. You start a context. It's kind of like for grouping. Whatever happens within that the run basically will be grouped together. So you load the data set, you start a model, you make a prediction. Now, in order to get the signature of the model, you call to that infer signature. You pass the input and you pass the output. It's like given this input, the model predict this output, create the mapping between. It's kind of like a reverse signature. When you got this signature, you can basically, depending on what library you are using, but MLflow.scikit-learn log model. And this is the model, put it in a model folder. The signature of the model is this. So when you do this, so this is done. Now on the left, models, it's going to take a second to load. Let's run the dashboard. So here, now on the top, the tab models. Oh wait, we just log the model. But, So you see here on top, register a model. So you basically decide, I want to pick. No. For some reason, let's see if the model was added actually. No.
Professor, so what is the inference looks like?
Inference signature?
Yeah.
So it gets the mapping, so I can print it. It's simply a prototype that tells you that the input should be in this value, the output should be. It's kind of like a signature of the model, input to output. I'm not sure why this didn't register the model. It says the model was registered. Maybe. So let's do one other thing. Going to try another test to not spend time. So this is the same example. I just changed the function, the evaluation function. So this is the evaluation function that we define. Everything else is the same. I'll save. So here we start the ML flow. Here the difference is that we are just doing Elasticsearch, like ElasticNet, and then instead of doing the auto log, I manually log the whatever I need to want to track. So if you use mlflow.log prom, you can manually one at a time give parameters that you want to log. It becomes key value basically. If you do mlflow log proms, this will require you, so you can just call this once and pass a dictionary of the metrics to. Either you do one at a time or you do dictionary. Again, the same thing. We do a prediction, get the signature. Now, here, it's kind of like it's the part I think was really missing. So I want to basically store the model as a model file, registered basically. So there are two versions here. So if the model address, the location that we want to store it doesn't accept file, it basically logs it this way. If it accepts files, basically log it this way. So depending on what we can do. So let's see. This is what's going on with the machine? For some reason, I'm not getting any. Huh. Wait just one more time. This is. Okay. And it's crazy. For some reason, lab one saves in lab two. I think it's just the direction. And lab two took a while to show. So all the model versions were added in the wrong folder at the moment. So, but if we, so if I go back here, and if I just run the ML flow UI. So now on the model, you start seeing the model, and because I ran it 3 times, so it ended up with 3 versions. So if you go to basically when you have here, so you can click on a model, and one is in production, one is it doesn't have a tag, the other one is archived, and these are all defined in the code. But you can manually change that. So you can pick a version and say that I'm not working with the new UI. I actually didn't like it, but anyway. So you can basically say, I want to change this from production to a staging. Then if you go back to your models, latest version is this. So if you go here, now you don't have anything. So you can say, I want to put version 2 in production. So what happens here is that when you are basically, now you need to automate this process. You have probably some tests that decide which one goes to a different version, different stage. That also could happen automatically this way. So in this part of the code, you go here. So you need to from ML flow, you need to basically do ML flow register model. You choose a model, then you have this ML flow client, which is imported somewhere up here. Let's just search it. Let's see the monitor, so please. Yeah, ML flow client. So using the ML flow client, you can, within your code, you can basically switch the basically a stage of the model. You just need the model name, the current version of the model that you want to use, and change the stage. Like you want to archive, staging, production, and so on. Now, if I change the ML flow, where's the new dashboard, which I'm not using it technically, they have changed the idea of model versioning, obviously stages that they define based on what they like. So now if you go on a model version, let's say this one. This is, now they have something called aliases. Basically, we haven't defined anything. And then you no longer can switch between different stage that easily. It's kind of like they create their own definition for switching between models. But I personally we just stick with the old UI because that's the definition we are going with. But for you, you can decide how you want to define this.
So for earlier, you said the main use is to maybe experiment between different model types. So would that be in the beginning of first time trying to build a model, or is this mainly ML?
No, that's a great question. So let's go here. So if we go back to experiments. Now, so let's say you're working on something, you're building a model. And every time you run a model, there's no need for you to choose a stage, anything. So you're just building different models. Your goal is that to compare these different models and then come up with a model that is a good candidate. So right now we have all of these models. So so you see these are XGBoost. One of this. No, it's funny. This is created 2 days ago. I never ran this 2 days ago. So one of this, if we can pick a run, to run, and we'll compare. So basically, you pick series of models. Let's say you build a bunch of models, and you build this comparison among them. As part of those comparison will be a pass toward making a decision. Should this specific model, or the best one here, goes to a next staging? So a staging means, so first time is none, then you go to a staging. Staging means that this model is a candidate to go to production. When you switch a model from, in teams are like this, when you switch from a staging to production, sorry, from a none to a staging, someone in the team, like the team lead or someone, says that, okay, we know there is a candidate, right? If this is the part that if you are doing certain things manually, then they will run certain tests to see that, okay, should we go to production or not? If the production approves, then we go to next. But you can later in your pipeline, when your experimentation is done and you have figured out your pipeline, this could be automated process. So it is switching between model and choosing different models.
So in this stage, we have the same data set because one thing confusing is, so we deploy our products and we see the accuracy has been dropped, and we're gonna retrain our model with the new data. In this like comparing model, we have a same data set.
So that is great. What if our data set has changed? Can we compare? It's like apple to apple comparison for two models. So I think the idea, the way that you need to look at it is that I had a model fail, not fail, let's get the decay. Now I have a new model, but new model is still like, it's not like you just develop one of it. Maybe you develop 5 of it. Which one of those 5 goes to the next? Either way, one of those 5 will go to production, right? So you need to decide which one goes. So that this is part of the comparison on what to select to go to it next. If you don't have a model decay and you just basically has a cycle of like, we need to update the model, or we need to do a comparison, we want to do better. Most of the time you have a fixed test data that you compare against as a baseline. Like your previous model was tested against that, your new model will test against that, and then there are like some performance, like a CPU memory footprint and stuff like that. In general, all of that could lead to a decision. But if you have a scenario like data has changed, your model performance went down, that means you are anyway, you need to spend time build the model. Now, the part that you spend time to build the model, that experiment, you can automate it this way. Basically. So there is a lab. I'm looking to run that. If you yourself, when you run it, if you run the lab, sorry, my mouse is lost. If you run this one, which is starter.pyronb, this one specifically does hyperparameter tuning. As part of the hyperparameter tuning, we basically, maybe actually, we just, let's just do this. Run all. So there's a data cleaning. I'm not going to talk about that part. Then comes here. So this is just building a baseline model. Now we want to, let's say you want to build a model and you want to hyperparameter tune. Okay, and here we want to do XGBoost with hyperparameter tuning. So the first thing is that I'm building a wrapper for scikit-learn. Because when I want to save it, I want this wrapper to have a specific function called .predict instead of .predict probability. So basically I build a wrapper for scikit-learn. The next thing here is that you need to basically start the context. So you start the context, we do random forest classification and basically wrap that random forest classification, you build a signature for it, then you store conda environment in this form. So sometimes you want something like you remember in the Airflow lab in the Docker composer, there was a part that says additional pip environment. And you basically, that was where you change the Python packages. Here you have the same thing, additional conda channels, basically additional conda dependencies, stuff like that. Some stuff maybe MLflow doesn't capture, and you want to add yourself, so you can basically manually add it like that. On the other end, basically, you can wrap the entire model that you have at the last line, MLflow PyFunction. I want to log this model, call it this, wrap it as with the wrapper that I defined, use the conda environment that I defined. This kind of becomes a manual process, and use the signature. Instead of doing MLflow does everything for you, specifically, you know what you want to wrap and build. So this is just the definition of that. Now, this model has the following feature importance, which that's not the goal. And that's the run ID for the model. So let's go here. So, and this is, again, this was how you could transition model to different stages. I'm going to pass all of that. Never reached the situation. So something great. One of these 9 should be wrong. I haven't reached here. Okay. Anyway, so we want to do hyperparameter tuning, but we want to use a library called hyperopt. So you do from hyperopt import fmean, TP, HV, spark files, and so on. It's kind of like what we are trying to do. We want to do a hyperparameter tuning using a function minimization, because you minimize, your goal is to minimize the error, either fmean or fmax. Now, because we want to do it to be fast, we are also going to use it with the Spark, PySpark, basically. We're not going to go over those ones. So we're going to, from MLflow, get the XGBoost. And then here is part that you define the search space. So these are all the parameters, hyperparameters that you want to search over. So you need to define, like for max steps, it's going to be integer, and it's going to be uniform between 4 to 100, increment by 1. Then you go learning rate. I want it to be it's hyperparameter, basically is a log uniform. It's going to be between -3 and 0, and whatever. Log uniform and so on. So you need to define for every one of this how you want this parameter to be. For example, for objective is binary. It's just we're going to use logistic. So it's just one value. Otherwise, you could pass it as a list. So you define search space. Then you go here. So here, basically, we want to start a run. You can build this function. This function does an auto log here because we want to log everything within hyperparameter search. Again, XGB basically requires data to be in a certain format. So you do XGB dmatrix to put the data in a format that XGBoost is required. And you do a prediction, you infer a signature. So this is just if you give it the parameter, you run the XGBoost. So here, XGBoost.train, you see it gets parameters as an input, and then basically it trains the model. This is assuming you have the optimal parameters, correct? We haven't done hyperparameter tuning yet. This is just a function that when you give the final set of parameters, it will train the final model for you. So close this. And where is this? Here. So here, basically, we want to use PySpark to kind of like speed up the hyperparameter search. So what we do, we from PySpark import Spark context, Spark configuration. So you build a configuration, sort of like a config file for the PySpark. But similar to what you saw in the previous class, PySpark needs a metadata storage. How does the grouping happen? Spark context. Remember, the context is a grouping of artifacts and the events that basically have that code run. So the Spark context, you pass the configuration, so you're initializing this Spark. So this was running on. So this tells that I cannot run two contexts at the same time. I think the previous time when I ran it, it's still running. But it did run. Yeah. So output is collapsed. So here, the way that you run it, you start Spark trials. We define how many, like your parallelism, depending on how many CPU cores, for example, you have. Here, put 10. Then you say with MLflow start run. I want to do find the best parameters. Fmin function, it basically what it does, it's finds the parameters that minimizes the function, the value of the function, fmin. What is the function? Function is train function. You remember we created train function on top, which gets a set of parameters and create a model. A space is the entire search space that we define. Algorithm TP that suggests basically samples from this search space, pass it to the train model function, gets the final result. Maximum evaluation, we want a 96 iteration. And in order to run this, we are going to use a Spark trial, which is that parallelism basically we define. So you let this run, and it basically starts running like this on your machine. You know, it's kind of like different runs. So also when it's run, because this runs in parallel, the numbers that you see are not in sequence. Basically, they're all over the place because one run might take longer than the other run. So that's why you will see different numbers. But you will see in front of it a validation log loss. And maybe I need to minimize this because it's like it ran for so many times. Okay. And then you get the final best run. And we put that in a different in a stage. I'm not going to do this part, sorry. Where is the? I just want to run this first, then we come back to that part. So now, if I so now you see all these XGBoost models. All right. So it's this is where it comes from, the hyperparameter tuning. So you can pick one. So basically tells you that for that certain set of parameters, this is the validation log loss, stopped iteration, and so what's stopped iteration? When you do hyperparameter tuning, you decide at certain operation that is enough. This is a good or bad, and you go to the next thing. So you can pick all of this. This has become such a challenging process this semester. So you then do a compare, and you basically. Those are everything that we. I'm just randomly selecting. Whatever we selected as part of the hyperparameter space, you can select those, and you can compare the runs against each other. And that's where basically it gives you some sense of which direction maybe you should increase the search space for a certain parameter or decrease it. Because if everything, for example, tells you that certain the max depths basically tells you that all the model search kind of lean toward the max depth. That tells you that, okay, by default, the algorithm was telling you the maximum depth has a better performance. So maybe you can increase it if that's not the max depth. So you know what I'm trying to say. It's kind of like gives you some information around like a parameters. Like for example, regular this alpha. You can pick one of these, like maybe the one that lets the highest performance, and the one after it, and see if there is a relationship. Should you change the alpha range, or should you basically leave it as it is? Anyway, so I'm going to close this. I'm going to leave that for yourself to try out. It's an easier process for you to do it yourself. What we want to do quickly is going to be TensorBoard. A quick one. So for TensorBoard, basically what I'm using here is their own library, like their own collab. But basically, if you work especially with TensorFlow, if you basically run this code, all you want to do is that at the top of your code, when you your TensorFlow code, you use that line 2, load x TensorBoard. You need to have pip install TensorBoard, and you just need to run that on top of your code. And after you run this, it's like the model will be trained, and this is basically how you load your TensorBoard. Basically, like a like a special prompter for Jupyter TensorBoard log directory. You need to pass the address of where the artifacts are being stored, or the logs, basically. When you have that, should be finished now. So when you run the TensorBoard, zoom out. It also gives you a dashboard like this. Now there's a difference here. So on TensorBoard, the information that you see is more like around neural network. I haven't worked with scikit-learn and stuff like that to see if it works, but it basically tells you this is the bias values. So you have different layers. Layers has different nodes, and you have this basically biases for them. So that's the bias distribution. This is the accuracy versus epochs. So you have epoch learning rate, epoch biases. Then you have validation versus iteration. On top of that, you can also you go to a scalar. You can basically select. You can access basically to a scalar part of your model. You can go to graph. I'm not going to go over this error, but normally this is supposed to show you the graph visualization of your neural network. Now it tells us to go to GitHub, issue 1929. We don't have time for that. Histogram, basically this shows you the distribution of weights and the matrices, weight matrices that we have per layers. So if sometimes, so that's distribution. This is histogram. So if you're interested sometimes to understand in layers of your tensor, like a neural network model, how are the weights? Is there basically a way that I believe that, I don't know, my model is diverging in the wrong direction, or one layer, do I need to do layer normalization or something like that? So you can see all of this in one go. And normally this is really useful when you run it on a large neural networks, because the amount of information that you get is not going to be that easy to you manually to extract. So basically use something like TensorBoard is really good. But again, that you can run it yourself. And this one is much simpler. WAND, or basically WNB. It's kind of like a one-liner also. So just all you need to do is that install it. Import VanDB, or is it WNB. You need to do a login. That means you need to first create an account on the platform, get an API key, connect your laptop to it. If you use your Gmail, I think it's 30 days trial. If you use your Thyssen account, I think you get a free trial, like a student account. So do this, do a login, and then here basically what you will see is that in order to connect this, similar to MLFlow, you need a project definition, like a run definition. So VanDB.init, this is the project that you want this data to be stored for, and it's called XGBoost. So it's just simple like that. The rest is just a simple Python code. And what happens on the bottom, you run the code and run everything. So here, run.sum. So basically, sorry, here, this line, vandb.config.update. So these are the parameters that you want to update. So basically, you create a dictionary of parameters that you want to update. vandb.config.updates.parameters. Then you run a model. Then you run .summary. It's kind of like they're like a JSON file. Error rate, you save the error rate. vandb.scikit-learn is a connection for scikit-learn. Plot confusion matrix. This is the test, this is the values, and run.finish. So it's just as simple as that. You basically do this. This will run, connects to your VanDB cloud basically storage that you have, or the dashboard basically is there, and it writes everything to it. It has this run history on the bottom, basically gives you some summary. Here, if it gives you access to the project and where this is stored at. So if unfortunately I can't do it, I tried it today and it told me that your apply for academy, it's like expired. So you just try it yourself, but it's pretty straightforward. VanDB is exactly like MLFlow concept. You need a run definition and a name for it, and log the parameters and log the model. There's a little I will say that the default